network traffic models for smart grid, and you can find some in the literature, but it always depends on exactly which of these functions are considered, these different applications. I think so far, or at least a couple of years ago, when we did a study trying to find out what traffic models exist, then the focus was mostly on this AMI type of functionalities, maybe some simple demand response or demand side management, home energy management, that you have a little bit of information going to and from the home, this HEMS device. But when we start to go into this wide area situational awareness, then it's more unsure how things are or will actually work, because this type of system, right now it's used at the generation and transmission level, and you have I would say relatively few points that are connected with optical fiber, and then you are transmitting measurements very often. But you can do that because you have optical fibers and gigabit links. But if you start to talk about wide area situational awareness down to in the distribution grid, then it's a different thing. And this case study I will show in the end, we did consider this and actually build our own protocol from different blocks. And also one partner was developing this measurement device that we used. So maybe it's not super representative of all such solutions, but it's one example of what exists. Yeah. But let's look a bit more at these different applications. Yeah. So the first one, this wide area situational awareness, it's also known as wide area measurement system, this name WAMS. Yeah. So it's monitoring and control across a wide area. It will usually incorporate SCADA systems, and then you also have these phasor measurement units. And these are what is currently, at least in some places, they are deployed in the transmission grid, and they take very frequent measurements of current and voltage angles and magnitudes, and you have time stamping based on GPS, so you can actually measure what is the offset in the angle, and this is what you can use to ensure that the frequency is the same, but also that the offset, the phase offset, is the same. So you can use this to somehow control this in the power grid. If you have too much wind power, for instance, then this may become too offset, and then you can detect that and try to counterbalance before it goes wrong. Yeah. So here's an illustration. So in this illustration, actually, it seems that this is wireless, and this is a very good question. Can we actually do this wirelessly, or do we need optical fibers? And yeah, I will come back to what are our experiences with this. Yeah, from an American point of view, there is this standard, and IEEE has this C37118 that defines a frame structure. It's actually a very simple frame structure where you have some header, and then you have timestamps and an ID of this PMU, and then the values that are measured of these different parameters, and then this is just sent usually I believe like an Ethernet type of frame, and they are just being pushed, these small frames, and it's in the US I think it goes these measurements are sent usually at 60 Hertz, so 60 measurements every second, but I think you can even oversample and do 120, and in Europe it would be 50 Hertz, and so some different numbers instead. And the critical thing when you're using this in the transmission grid, at least, is that the delay or latency should be low enough so that a report is delivered before the next report is available. So I guess this is what they mean by real time. And in that sense, if we can remember this definition, then for the case study we found that this was actually not possible with the measurements that we did. There was a quite large latency of the network, so there were many measurements, you could say, in transit when we received one measurement, so the actual state of the system had changed many times, or could have changed. So for each of the applications there will be some tables like this, and so the traffic type, it's periodic, frequent traffic, and then some requirements. And I would say this is it's a very simple traffic model. It's not something you can. It's not specific enough, I would say, that you can really implement it in a simulation or something like that. But at least it gives some idea of this. And in the literature, you will also see different interpretations of these traffic models. Then actually I was considering if someone could explain to me what does reliability mean. If we say that we need 5 or 6 nines of reliability, how do you interpret that? Alex, maybe?
I would say it's the probability of receiving a packet given in the latency that has been defined, right?
So just for one. So for one packet, what is the probability that you receive it? Or because it is a bit tricky. That's why I want to maybe bring it up. So in a practical system, how would you interpret this? You have a.
I think in a practical system, when they are talking about reliability, they are mainly imply availability. So they define reliability in terms of how many minutes, let's say, in a year we had an outage. Usually that's the way they do it in practical systems.
Yeah.
Which is mainly availability, not reliability.
Yeah.
But that's what I have seen.
Yeah.
Not in smart grids only, but in general networks.
Yeah.
When they're saying 5 nines, it means something like, I don't know, 10 minutes a year or something like that.
So when you say networks, do you mean communication networks or power networks?
Communication networks.
Okay.
Yeah. In order to distinguish between them,
Yes.
for power I use the term grids,
Okay.
and for communication I use the term networks. So we're the same, because it can be confusing. Yeah.
Yes, it can.
So grids and networks.
Yeah.
And
I learned the hard way.
So I guess something like that.
Yes. Yeah, I think you're right that often it's confused with availability. Yeah, and availability means the probability that you can actually access the system when you need it. And yeah, and the reliability is that is basically when you have accessed it, then what is the probability that it will function for the duration you need, or that your request does not take longer time than some deadline. So that would be transmitting a packet, for instance. Yeah, when you have access to the system. But then also this doesn't really say what is the time scale we are considering this, and is it like a moving reliability, a moving function we need? What if we have 10 packet losses in a row? Is that acceptable if we just look at long enough history? So in my opinion, when something like this is specified, then it's not enough just to put reliability. There should also be some requirement on the maximum number of consecutive packets that are lost, maybe. So something like this. But it's very common that they just put a number, and also so this number, I don't know where they actually get these numbers from, because I don't know. No, because this wide area situational awareness, often you have some machine learning on top of this, where you take all the measurements you have received, and then you have a model of the grid, and then actually if you are missing some measurements, then it's maybe not a big deal, because you know a lot about the system, and you can determine then what are the unknowns. So for that, I actually don't think that it's very critical you have so high reliability. That was also the case in this EU project, that I was trying to find out what are the communication requirements before you can do state estimation of the power grid. And I kept asking these guys, and they said, we don't care if we're missing some measurements, we just estimate them, and it's fine. So I think in this case, if you just make sure that you have a little bit extra PMUs, then if you're missing a few measurements here and there, then you can easily estimate what is the state of the system. Yeah.
I guess at least for some applications like industrial automation, where you want to use, for instance, wireless communication to do some closed loop control.
Yes.
And then I guess when they mention this reliability, it's really like 99.999% of chance that a packet is transmitted within that deadline. And then I mean you have a very intensive traffic.
Yeah.
Then if lost packet will affect this, because you are in the very low tail of the distribution. So if you miss 2 packets in a row, it will really decrease the reliability.
Yeah.
It will affect that very much. But if you are considering like a massive number of devices that transmit sporadically, and then maybe you can take this number as a compound metric from all the devices that are distributed in the network, and then if I have device transmitting in this network in different positions, what is the reliability that a packet goes through in this network? So it will be more the network level that you are talking about, the reliability of a packet transmission.
So it's like an overall reliability metric. Yeah.
So I guess it might depend on case where you want the
Yeah.
reliability to be achieved. I don't know.
But then if you are considering an area with 100,000 devices, and then all of them except one work perfectly, one of them is down the whole time. Is that acceptable, or do the losses also have to be sporadic? That's
Yeah, but that's the thing. You will deploy a network just to make sure that that device works reliable,
Yeah.
or you deploy the network and say in this network here you have a base station here that covers this area. Devices that are outside, devices that are outdoor, if they transmit sporadically, they have a 99.99% of chance
Yeah.
that the packets go through. But then you need to make some agreements with the customer, like, okay, if you are indoor, if you put your device into your elevator or into your chamber, a lock, it will not work. It
Yeah.
will not guarantee this reliability. So
yeah, but it's
it should be defined by contract, I guess, when you come to the deployment of these technologies. Okay, you sign a contract. Okay, this is my traffic type. This is my packet size, and then I guarantee this reliability.
yeah, yeah. But it's always good to keep in mind that there are many aspects of this. Yeah. Then the next application has to do with distributed energy resources and storages. And here actually we have this interface towards microgrids. So a microgrid is a part of the power grid that that is in principle able to operate independently of the power grid. So it doesn't necessarily rely on getting power from external sources. Maybe the power or this microgrid has DERs or some, so that would be wind turbines or solar panels or batteries and so on, that it can actually sustain itself for some period of time. And this is what is called the islanded mode, so that it doesn't have ingress or egress power. But then, of course, in some cases, maybe it needs to be grid connected if there's no wind and no sun or something like that. So of course, these things need to be managed. So here's even a picture of a microgrid. Yeah, but I think I said more or less all this. So here you have the possibility to put it in islanded mode, so you don't have any in and outgoing power. There are some specific standards relating to this. I am not an expert on those. I think you have to be more or less in the power industry. But about the different messages that are then exchanged between the units. So again, this is something that's periodic event-driven traffic, likely. The latency ranging from 20 milliseconds up to 15 seconds. It's I think it depends very much on the situation, and you can see the data rate is very low. Again, this is something that we could actually support with a dial-up connection back in the days. I think one of the last generations was this 56K connection. Reliability is not that crucial here. distribution grid automation. So this has to do with monitoring and control for fault detection and power restoration. Again, this standard, you will see that a lot if you work on power systems. Yeah. So in substations, so the level in the distribution grid, then substations they were responsible for stepping up and down voltage and so on, and also you could have these safety relays and so on. But there you talk about these intelligent electronic devices that are basically computers in the substation that are doing these automation tasks. And usually they are connected internally by some Ethernet with these standards on top, and then connected by fiber. Yeah. But in this case, it's more event-driven traffic and can be mission critical. Higher data rates, higher reliability, maybe than before. But a lot of this is also internal communication. Yes, and here we have the one about monitoring of passive infrastructure. So I think what is illustrated here. So you might have some sensors located different by the different cables, and then you have aggregation of information, and then a different maybe wireless link here to some central collection of the measurement. So in this case, you probably have some wireless sensor network here, and then some I don't know, backhaul connection or a collection of the measurements in the next step. Yeah, so increased visibility and prevention of faults. And yeah, here you see the different types of communication technologies. So these are like wireless sensor network technologies. Yeah. Maybe it's good to mention here that in this case we have this massive number of devices and clusters, which ties very nicely back to the IoT challenges. That you will have a lot of these devices trying to connect via some wide area technology. So this is maybe the real challenge. It's not so much the low latency and high reliability, but just the ability to handle this large number of connections is the challenge. Then we have this neighborhood area network, and we talked about the AMI already, so tracking consumption, to be able to write out bills. Yeah, but as we discussed, more interaction will come in the future, so we need more communication means. So some protocols, so I know Kamstrup are using this wireless M-Bus currently, but also these new upcoming technologies, LoRa and Sigfox and so on, are very interesting to consider to collect information and send some limited feedback maybe. Again, massive number of devices. The data amount is not that big because it is quite simple with this consumption information, and yeah, the control information exchange is maybe not that much. Then one also important one is this balancing supply demand. So the idea is that let's say that we have if we are not doing anything, then the load profile of maybe a house or a neighborhood would look like this, and it could be that actually we are getting very close to the limits of the wires or the power cables. So what we would like to do is preferably to flatten out the load, and there are many ways you can do that. You can try to use dynamic pricing, as we discussed. You can have load control programs, or this exploiting load flexibility, or not just load flexibility, but also production flexibility. This means flexibility usually means that you can, you could say, in time you can push and pull when things are activated. So changing the schedules. For instance, if you're charging your electric vehicle, you plug it in at night when you arrive from home, and then it just has to be charged in the morning when you need to drive. Or maybe you don't need a full charge if you're just going to work and back. And then you can leave it up to the utility company to decide when your car should be charged. And maybe they will pay you something to have this freedom or degree of freedom. So there are some business opportunities in this as well. So by having this buffer that an electric vehicle could be, then you can flatten out this curve. And now we're even up to several minutes, so it's really not very intensive requirements. Yeah. So maybe this was actually what I just was talking about. No, actually, I don't know. So, in some sense, but here the point is that you actually communicate from the cars, maybe. So there are many interesting problems. I've seen some works also on actually so planning. If you're driving in your electric vehicle, then where do you want to charge it? And so having this whole planning framework on top. So not just assume that you're charging at home, but also when you're on the road. I think we have mentioned many of these. So now I want to give you a brief overview of the different communication technologies that are used for smart grid applications. But keep in mind that this is based on the view of IEEE a few years ago. So probably what you have learned the past days will also be relevant. So yeah, I mentioned optical fiber. So here it's also indicated for which of the domains they are relevant. So maybe just WiMAX. I think at least I don't see that much about WiMAX anymore. It was very hot a few years ago, but I don't know if are you aware if it's still alive or it has been taken over by LTE or something else? Yeah.
Basically, LTE killed WiMAX.
Yeah.
I mean, there might be some installations, let's say.
Yeah.
Mainly for fixed broadband wireless access. The mobile standard, they 16.t, and or the 20, was that the 20 I think, why grow they called it.
Okay.
Never really took off because
No.
LTE was already in place, was standardized.
Yeah.
I don't think they use it. Only for fixed wireless access, like a few years ago LMDS, so to connect a headquarter, let's say, with the central office, with the distributed offices, via wireless link, which is easy to install and
Yeah.
faster, more feasible, economically maybe, and that's it.
When was the last time you had Wi-Fi at work? 5 years ago? 7
Actually,
years ago?
I worked in Brazil in a company that contributed a lot to WiMAX standard.
Okay.
That was together with Nokia at the time that Nokia was still trying to look in both sides. WiMAX or LTE, it was not yet defined which one will conquer the market first. So, and then, but the infrastructure, I mean, they had a lot of infrastructure and everything. But actually, some companies, like for instance, mining companies, I know some example of mining companies that they want to own their own network
Okay.
for security reasons also,
Yeah.
and they, something that they could control, and they they acquired part of the infrastructure to maintain their own private network based on WiMAX.
Yeah.
But I don't know, maybe because it was cheaper to buy this equipment that will not be used anymore from someone else.
Maybe, yeah.
Nobody wants to use it every for free.
Yeah. But I don't know, there was this Vibro, I guess it was from
Yeah.
Korea, right? It was the
Vibro was
Korea.
standard actually for mobile, let's say, WiMAX, etc. But LTE was already there. So they abandoned the idea. The standard exists, but there are no products, so what's the point?
Yeah, the standard exists, yeah, but
Yeah, but in this book by IEEE from a few years back, they are really highlighting WiMAX as the rising star for for smart grid. And maybe there are some installations. I don't know, but you don't hear anything. I don't know how much I need to say other than just mention that optical fiber is widely used, at least in the higher levels of the power grid, transmission grid, and then, yeah, like in Denmark, in some places, also down to the consumer level. But it is expensive if you want to deploy it alone. But if you put it together with the power cables, then it becomes quite cheap. Then there is this power line communications. So one example would be a box like this. So you can see there's an Ethernet connector here, and you just plug this PLC modem in the wall, and then you basically have internet connectivity in this room. But actually there are some different types of PLC with some very different properties. So there is this ultra narrow band which can actually be used across many hundred kilometers. So this type of PLC, I think it's probably used on the transmission grid, that you can send information also on over the power lines.
Yes.
And then this narrow band, you can use that in a home or a neighborhood to establish a communication network on top of the power network. But I believe there are some challenges if someone is using a drilling machine or hair dryer or stuff like that. Then performance is really impacted. And then there's a broadband version here, which is also for home area and neighborhood area networks. So I don't know if you have experience with.
PLC is quite strong communication, Steve. But as long as they use in the local, because if we use the line and there is transformer between that line, so
Yeah.
the PLC cannot use PLC.
No.
But in this perspective of hand or hands, it's quite a good option. For example, like a building management system and how to communicate between the lights, each lights.
Yeah.
You can communicate because
So in principle, yeah, you could
Yeah.
have smart light or
Yeah,
smart
smart
bulbs
lights.
and
because if you use like a ZigBee or WAN, if we compare from the economical side, it's cheaper if we use a PLC.
yeah.
And the newest PLC program is quite good.
But I guess it might still be sensitive if you have noise in
Yeah,
the fuse.
now they introduce a new they call that a new filter. They
Okay.
say that the for the broadband PLC VPN that can reduce a lot of noise regarding that
Yeah.
when the drill is in the low level network.
Yeah.
We call it some electrical low pass filter or something like that.
Okay.
For AMI within Europe,
Yes.
it's used, yeah? Yes. Okay.
Yeah, actually in this project so in Slovenia, for instance, they use PLC a lot in apartment buildings. So there are different smart meters for each apartment, and they are then communicating by PLC to the substation, where then the consumption data that has been collected is being transmitted on the mobile network. And actually they're using GPRS in many cases, so this 2G technology.
So the substation is different to the aggregator or concentrator or something?
Yeah, it's a data aggregator in the substation,
Ah.
or maybe there's one per apartment building, or yeah. But this principle that you are connecting the smart meters by PLC. In some cases, you can also have the smart meters are individually connected with a GPRS modem, but of course it may be more expensive because you need another connector. But yeah, there are really many ways to
They
connect.
use GPRS GSM because now smart meter company they developing some new protocol. They call it, if I am not companion specifications for energy metering. So with this protocol, GPRS would be enough.
Yeah.
Collected with aggregators, and the aggregators collected by another.
Yeah, if you only need to collect information
Because
once
a lot
per
of,
day.
lot of smart meters deployed, right?
Yeah.
So the cheapest way and the quickest way to deploy communication with GPRS.
Yes. Yeah, there are, so in the smart grid, as I guess it has become clear that there are many different wireless technologies that can be used in the different domains. And there are actually some that have been developed specifically for smart grid application. Yeah. Don't know if there's so much. Oops. Yeah, so I just kept one slide from this presentation. So WiMAX was really seen as a big thing, but I don't think there's so much point in.
I guess that,
Huh?
I think we can replace LTE
Yeah.
here it will be the same message.
And now 5G.
Yeah, actually.
Yeah, and there are some like general directions that IEEE see as the future for wireless technology in the context of smart grid. So, yeah, higher spectral efficiency, higher capacity, dynamic spectrum access, heterogeneous network architecture, use of licensed, unlicensed, cross-layer protocols, software-defined radio, use of Wi-Fi, 60 gigahertz. I think, except this one, this is all what is also considered for 5G and the future wireless in general. And then there's just like an overview of the capabilities of different technologies. Again, this is probably a little bit outdated with respect to the 3GPP, so the cellular technologies, and maybe even for the POC as well. I think there, as you mentioned, there was some recent updates. Okay, let's proceed to this case study of this European project called Sunseed. It ran from February 2013 and through May 2016 or 2015. Yeah. So we actually had a 3-month extension of the project. Yeah.
Some deliverer didn't make it.
No, some field trial didn't make it. Actually, there were some misunderstandings on how to interpret the deadlines. That the guys that were producing, designing these measurement units, they had understood this deadline as if that was the time where they should send the boards for production. But the guys that were installing the devices had understood this as when the boards had been produced and tested and were ready to be installed.
Something like this always happens.
And it wasn't even lost in translation because they were Slovenes, all of them. Yeah. So we had 9 partners from 6 countries, and maybe that indicates that many of the partners were actually from the same country, Slovenia. Yeah.
I want to know that in what level smart grid operations define in this project?
Distribution grid.
Okay. So as far as I understand, the IoT thing with the smart grids is just in distribution level. And I'm afraid that this is the point that companies bring to the science. They just want to sell their products, let's say. And this is not the power system.
The distribution grid is not power system?
Of course it is, but this is not the whole power system.
No.
And still it's not clear for me that what's the point of IoT in the energy part.
Well, IoT is a quite, you could say, broad umbrella of wireless technologies, mainly that can connect things. So I guess you can also just talk about communication abilities in the smart grid. Yeah.
Then my question is that what's the difference between communication infrastructure and IoT?
IoT is just like a term covering some specific communication technologies right now. So it's, I think you should take it with a grain of salt. It's a buzzword that's hot right now, but the same things will be called something different in 5 years. I think, yeah. So it's not something persistent like wireless communication. You know what that is, and that's persistent. But yeah, I discussed with you during the break that 5 or 10 years ago, everybody was talking about pervasive technologies, and this is not something you hear anymore. Yeah.
On Monday we had an interesting discussion with Carol.
Yeah.
He was talking machine to machine is an enabler for IoT, and IoT is more into the applications that uses machine to machine communication of these communication technologies.
Yeah. I think I see machine-to-machine communications as like one corner of what is within IoT. So
It's an enabler for IoT.
yeah, you can say so. Yes. The part of IoT that is concerned with connecting machines with the specific requirements that they have, but machine-to-machine is maybe not taking, I don't know, measurements from a sensor in the ceiling every half year. Yeah, whatever. Okay. Yeah, so there was this European project with different partners. And we basically considered two main use cases. One was this demand response, as I talked about a little bit earlier. So being able to schedule activation of appliances in the home, for instance, so enabling this. And then the biggest part was this wide area situational awareness to enable that through real-time monitoring, and then some also control, but we didn't consider the control part specifically. But you could say it's an enabler for control also. Yeah, so we wanted to collect real-time measurements from these like smart meter devices or WAN nodes. So what we did was we had a widespread deployment of PMUs in the distribution grid, and we connected them using 4G and 3G and satellite connections in the cases where the DSO did not have a fiber connection available. If that was already there, then this was used instead. Yeah, so we considered two types of monitoring devices. Actually, it was not a Kamstrup smart meter, it was a different manufacturer. What is it? Now I forgot. It's something and something, or plus something. Never mind. But actually the most important part in this presentation is this WAMS node, or extended smart meters you could also call them. And they are able to measure the phases of the voltage and current, GPS synchronized, and then they are connected via one of these communication technologies. As I also said before, the PMUs are usually used in the high voltage transmission grid, but here one partner developed a version that could be used in the distribution grid. So it was an embedded system based on some Intel Edison platform. I think now it's even discontinued, so that's very nice. The system architecture looked something like this. So we have the measurement devices over here. So in some cases it was, here it's written micro PMU, so the WAMS devices. So they have this, they're doing the phase of measurement. They have an MQTT agent. So MQTT is protocol, a queuing protocol somehow that you put the measurements in there, and then it's responsible for actually transporting these measurements to this MQTT server. So it's via the communication channels and through the core network of this telecom operator. So Telecom Slovenia were also in the project. So they delivered the SIM cards and provided access to the infrastructure and so on. And then all this information was gathered in a database, and then there were some services. For instance, this distributed, let's call it power grid state estimation.
Distribution system.
Yes, distribution system state estimation. Yes. Which was a machine learning algorithm that could estimate what is the state in different parts of the power grid, given a sufficient number of measurements. And of course, one of the challenges was to find out how many measurement points do we actually need to do this.
Is it complementary to AMI, or is it kind of studying another?
Well, we didn't have these measurement devices in all homes. So they were put in strategic places, but in the distribution grid. So it's complementary, but also AMI, you don't have the phases, I think. You don't have real-time measurements of the phases of current and voltage. Or maybe you can have that.
For that specific smart meter maybe, or?
Usually smart meters don't have this information. You can get a lot of other information, but the phases requires this PLU. Yeah. Okay. And in the project we did some different types of measurements. So we have the WAN device, we have, in one case, the wireless modem, and then base station. And then actually we have three different types of measurements. One is this Nagios monitoring server, which is actually, it is connecting with SNMP to the modem, and the modem is actually pinging the infrastructure, so we can get round-trip time statistics. So we collect that using SNMP. We get this statistics also cell IDs, downlink SINR, downlink RSSI, and this RSRP. Then on all the way from the WAMS board, we are sending the measurements, the PMU measurements, and they are timestamped with a GPS timestamp. So when this measurement arrives at the database, we are taking another GPS timestamp, meaning that we actually can compare these two timestamps and get the end-to-end latency. So from here to here, we can do that from all the measurements that are being sent. And then there was some statistics on the base stations. I didn't include that in this presentation. So one important finding we found in the project was when you consider the round trip time. So if you're just pinging the modem or the modem is pinging the infrastructure, so you just have this very simple exchange. Then you see some round trip times. Yes, so for fiber it's 3.8 milliseconds. LTE it's 25.7. So this is out and back. UMTS is almost 60, and then satellite we have this 730. And for those of you who are familiar with these technologies, then I think it looks very reasonable. Then if we try to compare to this one-way delay, so basically the timestamp that is based on, yeah?
These results are real measurement?
Huh?
Based on real measurement? Or
Yes, yes.
Oh,
Yeah.
nice.
So a lot of real measurements.
Yeah.
What that, is it standard? Okay, that's the standard, according to the standard.
Standard deviation.
Okay.
Yeah. Yeah, and
Oh.
okay, but I think this is based on measurements from the whole field trial that actually covered 4 different regions in Slovenia, and in some of them the coverage was quite bad, which we will also see in one of my plots. So I don't know this standard deviation. It's not saying so much right here. But the important thing is when we compare to this one-way delay, which is like the difference between the timestamp from the measurement and the infrastructure, then you see for fiber, so if we take the one-way round trip time, usually, so you can assume it's just half of the round trip time. So the one-way delay we observed for our measurements, because we have this MQTT queuing protocol, we have a TCP transport protocol also. Then this one-way delay was actually 50 milliseconds on average, which is 25 times higher. For LTE, it was almost 100 milliseconds, this one-way delay for a measurement. UMTS 120 and satellite 500. So there's really a big difference. And considering that we measured 50 times per second, then this one-way delay of, let's say, 90 milliseconds for LTE, you can see there's really a lot of measurements in transit. So this was a little bit surprising to see.
It's a commercial network, so there are other users using the same.
Yes, but this effect, it's I don't think it's due to the load of the network or anything like that. It's this these protocols that was used to transmit the measurements.
This is one-way delay network.
Yes, but there's no.
Okay, you just dividing by 2 because the opening should take more, right? Because you have the scheduling request, scheduling graph. So
Yeah, but they are already connected the whole time because they're sending the.
No, but it's not saying that the random access.
So you mean
the scheduling request, the scheduling procedure.
Yes. Okay, so you mean this should not be exactly half.
No,
it should
yeah,
be
I think so.
a bit larger fraction of this.
For uplink, yes.
Yeah. Okay, but still, it's then maybe it's 17 or yeah.
Yeah.
It's still really a lot. Yeah. So this was a little bit surprising, and yeah.
Do you have some reference for this? I mean, we can access.
Well, there is a public deliverable from the project. But other than that, yeah, we submitted a paper for SmartGridCon, but the reviewers didn't find that the results were interesting enough.
But you are most interested on the Roundtrip Time values for LTE, is that it?
Why it is interesting for me because it's really useful.
Okay.
It's good reference.
But there are databases in the university that they recorded the round-trip time.
And accessible publicly?
No, it's from the university. It's not open. And okay, and also it's from the university and together with some mobile operators. So I don't know how open it is. It's still if you are working with the university. I don't know how open
There is this paper by Mads Lauritsen
yes.
where Yeah, there is a CDF curve of the latency in the whole of northern Jutland, right?
Yeah, whole northeast.
It's a.
The network.
Is it NetMap? Is it based on NetMap or?
I don't know.
I don't think so.
Last was collaborating
Yeah.
with Max, something like
There,
Yeah.
I think there are data that you can have access.
Here's just one example of like the time series where you can see the for one specific or two specific points in the network. Yeah, the thing is the one-way delay is measured from the device itself, and the round-trip time is from the modem that's connected to the device. So it's yeah, they have two different names, but they are in the same link, you could say. Yeah, so it's quite stable in both cases, except here. I don't know why the round trip time is so high. It's like in the middle of the afternoon. Some random fluke, I guess. Then some of my colleagues in the project did this sensitivity analysis of so the impact on round trip time of depending on the uplink SINR and the downlink estimated SINR. Or was it the other way around? Let me see. Because we can measure the downlink SINR, but for the uplink, they did some estimation of that. But basically, what is shown is that the round trip time is more sensitive to low uplink SINR than low downlink SINR. And this is important to consider when we have a smart grid system, because you usually have data going uplink in a smart grid system. So it's necessary to really make sure that you have a good uplink SINR, minimize interference, have good coverage, and so on. And then, so I made some statistics on the cell, so the connections of the different modems. So which cells were they connected to? Yeah, and the color shows the signal strength. So I don't know how much you can say from that, except that actually it's minus dBm. Yeah. But the important thing here is that that you can see there's actually changes. So like twice per week, the modem would actually change to a different access point. So you would have some variability over time. I don't know exactly why this happened, and the guys from the telecom also were not able to explain this. So yeah, it doesn't seem as if there's a specific pattern, except
like
that
for one modem or one device measured, or this for many of them?
this is for all the cells in the measurement data, or the data that we had gathered.
How many devices you had? Because maybe if you had just one device and you put it like in a cell entry between two cells,
No, we
that's
had-
why it happens.
No, but those are the cell IDs, so there were many cells. Right?
Yeah, so
I understand many cells, but how many devices trying
Yeah.
to connect to those cells?
well, this covers basically all the modems.
Okay, so
Or-
it's
no,
only
not all,
modems, I
yeah.
assume a lot.
It is a little bit, or maybe it's actually because we will have many modems potentially that are connected to the same cell. So I guess the reason why then all of them are changing to a different cell ID. Could that be that they are changing from 4G to 3G? Would that give it, if that's that is would be a different cell ID? Maybe, yeah. So, okay. Then that's explained. Yeah. Another view on the on this data, now I have plotted this one-way delay. I hope you can see the lines. So here on this axis I have the latency on a logarithmic scale, and up here is the reliability, or the empirical probability that we actually received the measurements within the time here. And in this plot, each line represents a measurement from a specific region. And as you can see, the lines are quite different. But they are similar in the sense that somewhere between 100 and 200 milliseconds, they seem to have this flattening out, right around 200 maybe. And this is where this is caused by the LTE and 3G connectivity. And then when we go to the further tail, so here there's not really anything to help it again, but let's say this Bonifica up here, we go to even higher reliability. Now I don't remember. I was just no, sorry, this is not interesting. It was this point I'm interested in the Kinesia region, because this is where there's in this region there was a satellite link. So around 500, 600, 700 milliseconds, you see an increase in the reliability. So for this region, for low latencies, the performance is really bad. But if you can tolerate up to like 1 second of latency, then it's already 99% reliability.
For this case, how would you estimate or calculate the reliability?
Yes, the requirement I said was that I want the measurement, or it's basically that the measurement should be received within this timeline. So I considered all the devices that were supposed to be operational, and then for every second I expected one measurement within that second. And if I didn't see a measurement within 1 second, then it was a failure, then it was not reliable. So before I was talking about 50 measurements per second, but actually to save space in the database, it was decided to only keep one measurement from each second. So that is one limitation we had to live with from the communication side. But the reliability is actually quite high, as you can see.
Were the transmissions made 50 times per second, or there was
Yes, the transmissions were made 50 times per second.
But only the saving of the data was...
Yes. So when the measurements reached the infrastructure, this queuing server, then the 50 measurements were sent to the state estimation tool, and then only one went into the database. Yeah. Then over here I have a detailed plot for each of the different sites, and then a curve for cellular, for fiber, and for satellite. So this Kinesia region was one where they had all three represented. So you can see the satellite here, cellular performance. So we reach 99% reliability at 0.3 seconds, so 300 milliseconds. And if we can accept up to 1 second, it's a little bit higher. And fiber, yeah, that's around 3 nines. And this is 1 second. Here it's quite high, fiber, almost to 4 lines, but otherwise it's a little bit more than 3 lines. I also did a reliability analysis, so considering the whole field trial, where this requirement that a message should be received within 1 second. Then I calculated the reliability per week, and this covers 37 devices. So this is the number of WAMS nodes that were active or supposed to be active, and then you can see how many of them were actually fulfilling either 99% reliability or 9% reliability. And it's actually not that far from each other. It's only a couple more that are all the way to 99. So, of course, in a operational system, you would probably want to lie all the way up here, but I still think it's quite good that we managed to get so many devices to work reliably, especially because one of the regions had shitty coverage. Let's put it like that. And then we have this thing here, so you can see no devices managed the 99% reliability, but more than 20 managed the 90% reliability. So it was because one of the servers, I think it was the database server, had to be taken down because it didn't have enough memory anymore to handle all this data and requests. So they shut it down, upgraded memory, and rebooted. And the downtime that this took meant that none of the nodes could reach this 99%. And now we are very soon at the end, so I think this is more or less the last technical slide. I did a traffic flow analysis where I looked at all the, or not all, I looked at some specific TCP flows from WAMS nodes. So over 10 minutes I captured all packets. Basically we had access to a server where the telecom did an optical splitting of the data that was belonging to this, an APN. So they somehow treated all the traffic for the Sunseed project specially, and this was then directed, a copy of the optical signal was then copied and sent to this server, so I could capture with Wireshark and then analyze this data. So over here is the different link types, and then the statistics on the number of packets per second in uplink and downlink directions, and the bitrate also in up and downlink. And as you can see on the fiber connections, there's really a lot more packets per second, but also the bitrate is higher, both in uplink and downlink. So it seems that there's a larger overhead due to protocol headers. Maybe I should explain it together with this. So here's histograms. So this one corresponds to the first line and this to this. So it's a histogram of the packet sizes. So smaller packets to the left and larger to the right. And if you compare this to some of those below, then you can see the packet sizes are to the smaller side. And this also goes well with this, that that actually fiber connections, the packets will be smaller. And I'm not completely sure if it's TCP or this MQTT protocol that does this, but there is some adaptation that when the link is as fast as the fiber is, the round trip time is so low, then you can easily send a lot of signaling also to optimize the connection, I guess, or to send data individually. As soon as it comes, you just ship it through because you can you have a short turnaround time. But if you go to the LTE connections, there are a lot of them here, then you see that the number of packets has reduced drastically, and also the packet sizes have become higher. You don't have these very small packets of 40 to 79 bytes. So I think at this point the acknowledgements and so on are being piggybacked instead of being sent separately. And yeah, as we go down to the slower technologies, then you see that packet sizes go up.
And what is the biggest one?
This one, it's 1,200 up to 2,500 something bytes. So in that case, I guess TCP will also adjust its these windows, how much data it sends every time. So it's
concatenating packets. These packets that are being buffered, they may be being concatenated and sent.
yeah,
Sent together.
yeah. So the measurements are being concatenated and sent in a big packet. Yeah.
And but this packet size is the SDU or it's in the higher layer? Is the MAC packet size or is the SDU?
It's the transport layer, I guess.
So it's after
But- But it's from 1200 to 2500. So I guess it's this maximum MTU of 1500 something bytes, probably. That would make sense. It's just Wireshark automatically uses these bin sizes, so I couldn't get a more detailed view. Yeah. So, yeah, we talked about what is a power grid today. We talked about what is the smart grid and what will it become. What are some different architectures or domains for smart grid communication networks. Talked about specific communication technologies, and then finally I gave you some insights in this European project, this case study. 3 minutes over time. So here are some references that the material is based on. So this IEEE vision for smart grid communications is basically the book the first part was based on. And then there are some specific parts where some other references were used. So this one for the PLC, yeah, and something about requirements. Yeah. And then this deliverable D53 is actually the one that contains all the measurement results and analysis from the project. Okay, so this concludes the first part, and in the end, in the afternoon, I will not be talking as much. So let's have lunch, and I don't know when was
1 hour.
I think
1 hour. So 56 minutes.